Today, we're going to dive into the fundamental language of physics itself, measurement. It's the tool we use to translate the entire universe from something impossibly small to something just unimaginably vast into a form that we can actually understand and build upon. But just think about that for a second. We have one set of physical laws that's supposed to govern everything. So how on earth can we create a system of description that works for both the tiniest little particle inside an atom and a whole galaxy swirling through space? That is a monumental challenge.
I mean, the numbers alone are just mind-boggling. A proton is about a femtometer across. The Milky Way galaxy is, well, it's about 100,000 light-years wide. That's a difference of 36 orders of magnitude. Trying to describe both of those with the same rulers, kind of like trying to measure the thickness of a single human hair with a yardstick that's only marked in miles. It just doesn't work.
So, to solve this impossible ruler problem, scientists had to get creative. They developed a language of measurement, a system with its own vocabulary, its own grammar, its own rules, all of it designed to bring clarity and meaning to the physical world, no matter what the scale is.
So, what's the very first rule of any good language? Well, everyone has to agree on what the words mean, right? In science, that means having standardized units. Without them, you just have complete and utter chaos. Yeah, it all comes down to being able to make a meaningful comparison. Think about it. If my idea of a foot is different from your idea of a foot, there's no way we can build a house together. If my second is different from your second, we can't launch a rocket. These shared standards are the absolute foundation for any kind of collaboration and progress.
Every language has its core vocabulary, right? It's nouns. Well, in the language of measurement, our nouns are the 7 fundamental or base units. These are the absolute building blocks for everything else.
And here they are, the magnificent 7 of the International System of Units, what we call SI units. You've got the meter, kilogram, second, ampere, Kelvin, mole, and candela. Every other physical quantity you can possibly think of, like speed or force or energy, they're all derived from different combinations of these 7. Speed, for example, is simply a length in meters divided by a time in seconds. It's that elegant.
But where do these fundamental words even come from? This is so important. These definitions weren't just handed down from on high. They're actually the result of this centuries-long quest, with scientists constantly refining the definitions, always trying to make them more stable, more universal, and, you guessed it, more precise.
Just take a look at the story of the meter. It started as a fraction of the Earth's size, which is a great idea, but really hard to measure consistently. Then it became a physical object, a special metal bar stored near Paris. That's better, but bars can shrink or expand. So then we moved to something much more fundamental, the wavelength of light from a specific atom. And finally, we tied it to an absolute universal constant, the speed of light. Each step was a massive leap forward in our ability to speak this language with more and more confidence. Okay, so we've got our vocabulary, but just knowing the words isn't enough. We have to use them correctly. And in measurement, that means you have to understand the absolutely crucial difference between accuracy and precision. And trust me, they are not the same thing. So what's the deal? Well, accuracy is all about correctness. It's hitting the bullseye. Precision, on the other hand, is all about consistency. It's landing every single shot in the exact same spot, even if that spot is totally wrong. And it's completely possible to have one without the other. To really nail this down, let's just imagine you're at a shooting range. The true value you're trying to measure is the dead center of that target. Okay, look at that first target on the left. See how the shots form a really tight, consistent cluster? That's high precision. But they're nowhere near the center, so that's low accuracy. Now look at the second target. The shots are kind of scattered all over the place. That's low precision. But if you were to average them all out, they're actually centered right on the bullseye, which means you have high accuracy.
And this perfectly illustrates what we're always aiming for in science. We want our measurements to be both precise and accurate. We want a tight cluster of results centered perfectly on that true value. When we get that, it tells us our measuring instrument is reliable and it's calibrated correctly.
All right, we've got our words and we understand their meaning. Now we need some grammar. In the language of measurement, our grammar is the system of significant figures. It's how we communicate to other people just how much confidence we have in a particular number.
Significant figures, or sig figs as you'll hear them called, are basically the digits that we can really stand behind, the ones we know for sure, plus one final careful estimate.
The number of sig figs you report is a direct message about the precision of your tool, and this is so critical. It's how scientists stop a tiny bit of uncertainty in one measurement from snowballing into a huge error in a final calculation, whether they're designing a new drug or aiming a space probe at Jupiter.
Now, the trickiest part of this grammar, it almost always involves zeros. A zero that's sandwiched between other digits, like in the number 101, is always significant. That's easy. Leading zeros, like in 0.053, are never significant. They're really just placeholders. But trailing zeros? That's where the language can get a little ambiguous. Take the number 1300. Did the person who wrote this measure exactly 1300, right down to the nearest meter? That would be 4 significant figures. Or did they just round to the nearest hundred, because that's only 2? Without any more information, we just don't know. It's grammatically unclear.
But scientific notation provides the perfect, elegant solution. It completely removes all doubt. Writing 1.3 times 10 to the third power is without a doubt 2 sig figs. 1.300 times 10 to the third is, without a doubt, 4. It's how scientists make sure that their statements are perfectly grammatically clear every single time.
So we have vocabulary in our units, we have meaning through accuracy and precision, and we have grammar with significant figures. So why does mastering this whole language even matter? Because it's literally the operating system for the modern world. From the microchip in your phone to the GPS satellites flying way overhead, none of it works without this shared, obsessive attention to detail. It's how we make sense of reality and then build amazing things on top of it.
And this language doesn't just help us build stuff, it gives us an incredible power of estimation. It's the ability to do these quick back-of-the-envelope calculations that can just cut through all the complexity and reveal some really surprising truths about our world. Let's try one.
That's right, $1 trillion, all in $100 bills spread out evenly from end zone to end zone. What's your guess? A few inches? Maybe a few feet? Go on, take a guess.
The answer is about 8 feet high. Isn't that wild? By just using the principles of unit conversion and estimation, the very language we've been talking about, we can get to this incredible and probably much higher than you expected result. That's the predictive power you get when you speak the language of physics.
So we've journeyed from the basic vocabulary of base units all the way to the grammar of significant figures. This language, which is built on the absolute bedrock of universal constants, lets us describe everything from a proton to a galaxy. So the final thought is this. As we keep refining this language, as we make it even more precise and even more fluent, what new discoveries and what deeper understandings of our universe are just waiting to be written?